Okay. So today's stakeholders pre-conference meeting, which is organized as part of our preparations for the African International Conference on uh, José Ignacio Latorre is a director of Center of Quantum Technologies in Singapore and a professor and post of chair at the National University of Singapore. He is a leading figure in the particle physics and quantum information with extensive experience in building national and international quantum research ecosystem. So today, Professor will share international perspectives and practical insights on how national strategies in quantum science and technology and are developed and implemented with lessons which is relevant to Ghana. So, ladies and gentlemen, please join with me in introducing or welcoming Professor Jose. Welcome for our meeting, and delighted to have you with us today. So, the floor is yours.
Thank you, Henry, and thank you, everybody, for being here. Can you listen to me correctly?
Yes, yes.
Okay. Also, more or less, I should talk how long? Just not to make a mistake.
So, maximum of 45 minutes is fine.
Maximum. No, I will use less. Okay. So can I share my screen? Yeah.
Yes, you can. Yes, you can share screen.
Okay. Um, can you see my screen now?
Yes, please.
Okay. Okay. Well, as I said, thank you very much for the invitation and to listen what we have done in Singapore. So I would like to start by saying that Singapore is a small country. It's 5.5 million people. We In Singapore, we do not produce enough food for Singapore. We don't have energy. We don't have water. So Singapore is very special because the economy must be based on added value. So we need science, we need technology, we need talent. Uh, all the economy is based on this idea. So let me tell you a little bit about quantum and CQT. Okay. So the first thing is that CQT is the flagship center for quantum in Singapore. It was established in 2007 as an effort to go beyond the level of the departments in Singapore. At the time, it was not internationally very high. So one of the fathers of the country had the idea of building research centers of excellence. And that worked very well. It was the first center of excellence, then there were four more, and now there were seven. Now we moved to a new level. We became a national center for all of Singapore, not only at the university NUS. And our mandate is to do basic and applied research. Our mandate also includes develop a lot of talent, PhDs, and also to work with industry. So we do a lot of projects with the industry. On top, besides the Center for Quantum Technologies, there are many other initiative programs, and we lead them. So people at CQT are responsible for the different initiatives. In big numbers, the Center for Quantum Technologies is made with 340 people. We have 25 principal investigators, so that makes that every principal investigator, as an average, has a tree of order of magnitude 15 people. We have generated quite a number of scientific publications. Our age as an institution is 180 in Google. We have generated 8 startups, although it was never intended. We have generated these companies. We receive a lot of visitors, both academic and also engagement visits, and these are politicians, different companies, investors, all sorts of people come to Singapore to know what is going on in quantum. Currently, we have around 100 PhD students and 71 interns. Now, we started to define a strategy for Singapore in the year 2000, and we went into a lot of discussions, and the fundamental idea is that it should be very simple. So there is only one national committee, which is a National Quantum Steering Committee, with all the possible stakeholders in the country. That includes from the universities to the Cybersecurity Agency, the Economic Development Board, which is to bring companies to Singapore, and even the Minister of Defense through DSO, which is the leg for research in the military. That's the first layer. What is the duty of the National Quantum Steering Committee? To define the guidelines and to provide the funds. So none of the researchers or the people implementing this strategy has to work hard to get the funds. The funds are guaranteed by the National Quantum Steering Committee. Then there is a second layer, which is the Quantum Office, which is all the programs are run in the Quantum Office. Now, what are the programs in the quantum strategy? One is the Center for Quantum Technologies. This is the basic science piece. Another one is Hardware Initiative for Quantum Computing. We have different sub-projects, but essentially the idea is that, one, we build our own quantum computers. We believe that exploitation bands will dominate the future, and nobody will sell a good quantum computer to anybody. So we are preparing for that, and in a modest way, but very forceful, we are making our own quantum computers. And also we are bringing what we believe is the best quantum computer in the world, is a US company called Quantinuum. We are bringing it to Singapore. So we will have 3 quantum computers made by us and 1 which is coming from overseas. But what do you do with a quantum computer? You have to run algorithms. So we have a large software initiative, enormous, that is devoted to advanced quantum algorithms and solutions, to hybrid quantum computing, and also to have a place where companies can come and talk to the scientists. And this is the National Quantum Computing Hub. Then on top, we have many others. I will not mention all of them. I will mention that we have a national quantum platform for communication, quantum communication. This is quantum key distribution and also post-quantum cryptography. We have also a sensing program and another, we fabricate our own chips in a foundry. And finally, let me mention that we have a large program for scholarships. We have very well-paid scholarships open to anybody in the planet, very competitive, but very well-paid. Now, again, for the science, the center is based on the 3 pillars that many people are organizing. One is communication security. The second one is computation and simulation. A third one is quantum sensing. But we also do basic science. We do quantum information at the basic level, and we develop our own advanced instruments. So we do single photon generation, we do switches, we do single photon detection, we do FPGAs, we work with lasers, anything which is needed, we do it. Of course, we run many other things, outreach, international collaborations, talent, industry, and we help to run the country through the programs I mentioned before. Just one piece of information on our science in communication. one of our spin-offs launched a satellite for quantum communication, quantum key distribution. The latest, the third satellite was sent a month ago. It is called Spectre, and it will deliver quantum key distribution on the planet Earth in different continents. We do post-quantum crypto, and we are working on quantum internet, how to connect quantum computers. For computing, we believe that nobody knows what is the future of quantum computation. So we are doing superconducting qubits, trapped ions. We are also doing neutral atom arrays, cavities, photonic chips, algorithms. And also we pay attention to energy, sustainable computing. For metrology, we have one of the best clocks in the planet. It's a lutetium clock of a precision of 1 part 10 to the 18, and a gravimeter that we can map the gravity of the planet, and we can detect faults underneath on the ground. We can detect, it's so sensitive that we can even detect clouds on top of Singapore. We have also magnetic sensing, NV centers. Let me go past the advanced instruments and basic science. And I will tell you a little bit more about quantum computing. Building a quantum computer is extremely difficult. You have to define the bottom, which are what is the platforms that you are using. And as I said, there are many platforms. Still, it is not clear which is the winner. We are working in superconducting qubits, in neutral atoms, in trapped ions. For photonics, we are not building a quantum computer because we think it's too difficult. We don't have enough capabilities for that. But then you have to talk to these computers with FPGAs, pulse level access, where you do error correction. And on top of that, you have the connection through the cloud to all the users. Again, at the very high level, we have fault-tolerant algorithms, and you again have error correction. For every one of these things, we partner with different companies in the planet. I've selected a few here, but we really work with a lot more. So again, for the quantum computers, this is just to make it clear. We are devoting a large amount of money. There are 65 million just to generate 2 of them, neutral atoms and trapped ions. And for the other, for superconducting, we already have a facility, and that is very good because we have already started to produce science with our own computer. This is the picture. This is a fridge of a superconducting computer. It is in our labs, and we essentially assemble every piece. For neutral atoms, we are building a real device. It's a little bit technical, but you have to trap ions levitating on a chamber, and then you address them with lasers. It's a very promising, very difficult way of making a quantum computer. And for trapped ions, again, we are building, as you can see, the pictures are real pictures, modest trapped ion device. Our plan is to have a first prototype in 2 years. We will then scale up to larger number of qubits in due time. As I said, all these computers need algorithms. But I would like to make a final comment on the hardware, which is repeating the fact that although now there are companies that would sell you a quantum computer, it is known that there will be exploitation bans. So in particular, as quantum computers get 300 qubits and a precision of fidelities of 4 nines, 99.9% of fidelity for every gate, then they will not be able to exploit it. For algorithms, we have organized our approach in a, let me say, more sophisticated way. We have primitives, that is basic algorithms. We have error correction. We believe in the next 5 years, this will dominate the research. And then for the very long future, fault-tolerant quantum computing. We have a horizontal, which is to use AI for quantum. And we have another one, which is simulation. So tensor networks, quantum-inspired algorithms. This initiative has 52 million Singapore dollars. Now, we believe in collaboration, not in competition. So our aim is to develop the computer. So we need an operating system. We need the middleware. For that, we're developing an open source, a sort of Linux for quantum computers, which we call Kibo. And we are working together with people everywhere, in Italy, Los Alamos, Abu Dhabi, India, Australia, Philippines, everywhere. Japan, sorry, everywhere. Actually, next week we go to Japan, and one of the discussions will be the development of Kibo. Let me move away from computation. I go to communication. Again, we believe in our own solutions. So we have started to deploy a network based on QKD, on quantum key distribution. And by now we have 30 companies working with us. And it is supported by one of the ministries in Singapore. We also connect to the satellite. We have the ground station to track the satellite. And at the moment, we are connecting all the universities, and we are doing demonstrations for the industry. To give an example, we did a backup for Amazon. And we also work with the Monetary Authority of Singapore, which is the national bank. This is a little bit more of detail in the sense that this is not new. We have been working on that for a lot of years. We started with free space communication in 2006, and we started to launch satellites in 2020. Now our satellites is shared with a consortium of countries. England, Canada are part of the consortium. This is again the communication. Why there is so much emphasis in communication? Because it is about cybersecurity. There is a lot of interest from the military sector, and it is a more mature technological. So it's an easy one to deploy because everything is there. And as you can see here, we are merging companies which are optical fiber, like Netlink, with all the universities, with the Fraunhofer Institute from Germany. It's again a very collaborative approach. For sensing, I've chosen to show you the gravimeter. You may have mining industry. So this is the machine. It's based on quantum interference of atoms falling. The advantage of a gravimeter of this kind is that the precision is 1 part in 10 to the 8 for G, for the acceleration of gravity, a microgal. And also, the important thing is that it is an absolute calibration. So many of the solutions that are in the classical side do not have absolute calibration. They fluctuate, they go off, and then you're not measuring the real thing. So our gravimeter has been tested. We took one island in Singapore and we map it, as you can see on the right, with plenty of measurements everywhere. So we do have a map of gravity of Singapore. It is very important for us to develop talent. Again, we are only 5.5 million people. We cannot compete with the large countries. So we have to do it well. The way we attack that is that we have a national quantum computing hub where a big section, the central section, you see the upper section is accessing quantum computer, hardware, middleware, and applications, but the talent and outreach are central to this strategy. We don't take lightly what is to educate the new generation. It takes years to educate a PhD. We have detected 5 levels of interest in quantum. The first is people that are simply interested. They want to learn a little bit. let me call them curiosity-driven people. Second, are people that want to change jobs, engineers that they want to work in quantum, job seekers. Then companies that want to learn inside. They don't want to share anything. They want somebody to go there and teach them professional courses. And then we have masters and PhD programs. So at CQT, we work on the 5 elements. And in particular, the very first, there is a web page, the curiosity driven, full of curated courses that we call qtalent.org. Anything there has been checked. It is very good people trying to tell what quantum is. There is no hype. There is no exaggeration or misrepresentation of what physics and quantum physics is. The PhD program is a solid piece, as I said. We have 100 PhDs, but we have already graduated 135. So we are, let me say, 235 people for the ecosystem, PhDs in quantum, which is not zero. And as it is happening, these alumni, these ex-CQT people are really filling the positions in the industry and also overseas. So we have a very good alumni network in all the countries in the planet. The alumni total is around 600 people. This is a way to show that our efforts work, because on the left, you see where the people that came to CQT to get their PhD came from, and then on the right, where they got their job. And as you can see, Singapore 12 and then 39, we are attracting talent to Singapore. We are also checking whether they are working in academia or in industry, and more people work in industry. I would like to mention now our relation with industries and startups. We have generated 8 companies, 3 in communication, 1 in hardware middleware, this is FPGAs, another 3 in quantum computing software, and 1 in sensing, atomionics. What is our way of relating to industry? We work with companies from all over the planet. And if the project we discuss is good, we write a document. And typically, we ask the companies to bring a minimum of 25% of the project, let it be in kind or in cash. And we bring up to 75%. This has proven in less than a year very useful. We have now contracts with IQM, Rigetti, Kisai, Maybell, SpinQ, Quantinuum, Amazon, IBM, Quandela, OCBC, the banks, Pascal, plenty of them. We believe that this is working, and now every project, every program we create, it has a piece of money for hiring people that we call core team. And then we have more money for translational. And what I'm showing you is the translational part. The core people guarantee that we have enough expertise in that field. As I said, the priority is to build the economy of the future, to build a quantum economy. We want to take our computers and we believe in ethics, we will be offering 10% of our computing time in quantum computers to work with other countries for free. And let me end up by saying that we have a geopolitical situation which is peculiar because we are near China. The language of the country is English. And then we are far from Europe and from US. But we keep a policy of collaboration with everybody, as you can see here. We collaborate with USA, with Europe, with China, with South Korea, with Japan, with the Middle East. So we believe, and hopefully we will be working with more and more countries. Recently, I'm preparing a document, the agreement with Chile in South America. So we hope to include Philippines, Thailand, and many other places. And this would be my presentation. And I think it would be good if you want to ask questions, then I can go deeper into the discussion.
Okay. Thank you very much, Prof. And we would want to get some questions from the participants. Hello, please. In case you have any question, you can raise your hands or just unmute your mic and then ask a question. I think there are no questions.
No questions.
Yes. Yeah, I think there are no questions. I'm not sure that I should wait for some few minutes and if okay.
Hello.
Okay.
Good afternoon. Thanks for the presentation, Prof. One to think about. So, in the context of Ghana, given how much funding that is gone into this, are we able to do or replicate the kind of thing that you're doing in Singapore?
I really could not understand well the
Okay.
question.
So my question is about the investment, the capital investment that has gone into this.
Yeah.
I guess it's very huge. So if we contextualize this in the Ghana's economy, are we able to do this to replicate the kind of work you've done in your area, in your space? And how would you advise us to progress or proceed?
Well, the total investments that every country is putting in quantum is very diverse in different countries. In US, a lot of the money comes from the private sector, not from the public sector. There are many companies that are developing quantum. In other countries, like, let me say, France, there is a lot of public investment. For Germany, okay, a lot. Supercomputing centers are buying quantum computers. In some countries, it's very small. Italy, it's small. Singapore is very singular. It's very large, the investment per capita. Okay, we are talking about the amount per capita. I think, and then on top, all these things are national level programs. It's not a university program, it's not a team program, it's not a grant, it's a national thing. So that then it depends on the politics of the country. If the country decides that they want to develop know-how in quantum, then they put the money. If not, they don't put the money. The order of magnitude that in many countries you will find are between $100 million to say $300-400 million in many countries. Is that a lot? It's a lot for a university. It's a lot for physics department. For a country, countries are big. An airport is much more expensive than that. So it's a political decision how you want to have priorities, and then it has to be decided at the top level. Do I think that countries can put this money? Yes. I'm now, for instance, in contact with Chile, and this is not a super rich country, and they are putting money. They are investing seriously. Other countries that are little by little starting to put money that were not in the map before is Korea, for instance. Japan and Australia have always been putting money, but now all the Southeast of Asia, well, there are more and more interest, and there are startups popping up in different countries. So your question, which is about the total amount of money, I think has to be taken in context with the politics of the country. Okay, Singapore has no doubts they have to invest in the future. The future depends on the technology you have, not on other things. Whatever is traded today in 20 years may not be traded. Okay. The companies that dominate the planet are all in software, classical software. 30 years ago, it was not like that. So the economy is moving very fast, and it's about to be a player in the future.
Okay. All right. So in in context, it has to be a political decision that has to be made.
Yeah.
And so at the level of the university and then research centers, what would be your advice in terms of putting some kind of initiative together?
So I think at the level of universities, it's about talent. Okay. So the best is to develop a good undergrad curriculum, modernize it, take into account everything which is going on, and then try to connect with other universities to send students in periods of time to learn new things, okay? So that in a few years they can come back and they can bring all this knowledge and make it bigger. I think this is happening everywhere. If you look at how many countries are attacking the problem of quantum is by creating fellowships for the best students in their universities to go and learn more in other countries and then call them back. Otherwise, it's very difficult. You want to make an ion trap. Well, you really need to know how to make an ion trap. It's something which is not at all trivial. It's very difficult. So you really need to send the people to learn when they are getting their PhD or at the master level. And we see that all the time. As I said, we had at CQT, we have students from Philippines, we had students from Peru, and these people are sent by their governments so that they learn, and then they are sent back, which is exactly what China did 50 years ago. They started to send students to very good universities. Now they collected them back, and now they are building everything. Okay, so the game of science is not a short-term game; it's a long-term game. So have to play the long-term game. Universities should prepare the talent.
Thank you. Very good insight. A journey of 1,000 miles begins with a step. I guess we'll take it step by step. Thank you very much.
Thank you.
Okay. Any question? Any other question? So I think we can go on. So thank you very much, Prof, for the insightful presentation. So I think we can then move on. If there's no other questions, let's move on to the next section. Thank you again, Prof, for honoring our invitation, and we look forward to meeting you.
Bye-bye. Bye, everybody.
Bye. Bye. So, thank you, participants, for joining. I want to make sure that we have any announcements from Dr. Martin. Hello, Dr. Martin. Okay. So I think we'll just proceed. So thank you for joining for this session. We would have a meeting next week, the same time. And before we leave, I think we'll take a photograph, a snapshot, selfie. So if you can on your camera, then we'll just take a quick snapshot, then we'll go. Okay. Give me some few seconds. Okay. Okay. So give me some few seconds. Let me try again. Okay. Thank you very much for joining today's session, and see you again next week. Bye-bye.